Okay, we'll get started in just a minute or two. We'll get started in just a minute or two. Again, a reminder, if you keep your cameras off, they don't get a whole bunch of things on my screen. I appreciate it. And we'll get started in just a second. Gives everybody an opportunity to get in. Again, a reminder that if you need to ask questions, there's the chat box. You could type your questions in there. So again, we'll get started in just a minute or two. And again, if you need to ask a question, the chat box is there. And a reminder, you can send this to everybody or just me privately, and I'll try to see the little private label, type something back to you. And again, if you could just keep your videos off, that would be great. Yes, there's a couple of questions about the exam and the homework assignments. My anticipation is that we will take the exam online and we'll do it through Canvas, and you'll take the exam through Canvas, and then there'll also be like an assignment little box that you can upload your homework. Kind of like maybe what you do for lab, you take a picture, scan it in as a PDF, and on that day when you take the exam, you then can upload your homework. And my guess will be it will be through Canvas, and there'll be problems where you'll do the problems, obviously, and probably try to do my best to format it similar to our regular exams. And for problems that do have work associated with it, you'll also need to kind of work that out on a piece of paper and also upload that with your exam. That way, because it is a computer, it's only going to take one answer. So in case you get the answer wrong, at least if there's work associated with it, I could take a look at your work and try to give you some partial credit and stuff like that. My understanding is that your grades in this class is still going to be like normal. And I don't want to tell you anything incorrect. So I would definitely look for emails that come from the college and maybe missions and records and that type of stuff. And again, I teach at a lot of different colleges. So there might be other options available to you that are not normally available to you because of the situation. And again, I'm not 100% sure what those options might be, but my understanding is at this moment, I believe everything will be sort of graded like normal. I guess, you'll get a letter grade is my understanding. So in terms of accommodations for anything through TSPS, for example, the best I could do is obviously extend the time if you do have an official accommodation. Obviously, if we take the exam online, I should be able to accommodate you in that sense of the extra time. And again, obviously, if you have officially went through the services program for that, we'll do our best to get you that accommodation. In terms of will the exam be pushed back or not, if my understanding is, if I'm trying to remember off the top of my head without looking at it, I think we need to get through chapter 8 would be the last chapter that will be on the next exam. So if I had to guess, it might be pushed back a little bit. So look at the schedule. So I'll give you an update on that on Wednesday. I had an opportunity to kind of look at the schedule and sort of see where we're at. If I'm not mistaken, it might be scheduled for next week, the exam. But we'll kind of see where we are, kind of like normal lecture, kind of see where we are, at the end of the week here, and we'll talk about in terms of the exam. But online seems to be probably what it's going to be, and that's probably how the exam will be. You'll log into Canvas, you'll take the exam. Online, for problems that have work associated with it, you'll write the work out on a piece of paper like normal. And after you submit your exam online, you'll then upload your work. And again, I'm going to do that so that I can then go back and again, if you happen to put the wrong answer or typed in the wrong answer, at least if you have some work, I could kind of adjust your grade. So it will typically, in terms of the timing, and again, I'm still working out some of these things, but so 4/8 would be next week, would be my guess. So it may be pushed back a little bit. Again, we need to get through, I think, chapter 8 still, which is the next chapter after this one. And usually it will be open for a period of time for you to take the exam, probably around when we normally would have lectures. When the exam probably will be scheduled for you to take during that window. And you'll have a certain time period to take the exam. And obviously, just like our normal exam, you'll have a certain time to actually take the exam when you do it. Yeah. So again, for uploading and stuff like that, we'll maybe talk more about this as well a little bit later. But you could use a picture is fine. However, you need to do to get it up online. Again, on your phones, on most phones, your Android or iPhone. I know a lot of schools, you could probably get an app to do that for you. I believe Adobe has one. It's Adobe Scan. I saw that come around a lot as everybody was transitioning. I think it's a free app that you can use on your phone, and it'll essentially use your camera and kind of scan your papers and then turn it into a PDF file, and then you could upload it. So again, Adobe Scan, I think, is one that I've seen come across a lot, but you don't have to use that one. But probably the easiest way if you don't have a scanner would obviously be find maybe a phone app or something like that that will turn your pictures into a PDF. Yeah, so Cam Scanner, same idea. I think it works kind of the same idea. So I know there's a lot of apps that will sort of do that for you, and that's probably for most people. Even me, I'm not even sure where a scanner would be around here. That's probably the easiest way to do that. Okay, and again, like normal, we're going to kind of keep lecturing, and then we'll talk about the exam and all that, and probably more on Wednesday we'll talk about the exam, and if it is scheduled for next week, which would be next, based on what you said there, next Wednesday, we'll kind of see where we're at, but my guess is it probably might be moved back to the next week after that, would be my guess. Again, it's based like normal, and that's kind of finishing the material so you can do the exam. So with that being said, I think we should start going here so we can actually do some lecturing and all that good stuff. So we were talking about solutions when we last were together and lecturing, and I believe we finished up talking about sort of percent concentrations, and now we're going to talk about really molarity, and molarity really is the most common unit of concentration, and molarity is that unit that you oftentimes will see on a bottle, and its molarity is big M, and big M means basically moles per liter. So when you see that number or that letter on a bottle, it stands for concentration. That usually is the most sort of common unit of concentration that we come across. So when we calculate the molarity, it is basically the moles of solute over the liters of solution. So when we talk about molarity, big M equals moles per liter. This is also can be thought of as a formula, and we basically can use this just like any type of formula and solve for any one of those sort of variables that are there. We can solve for moles, we can solve for liters, we can solve for molarity. So for example, if we wanted to solve for liters, it would equal moles divided by the molarity, again multiplying the L to the left and dividing by the M. If we want to calculate the moles, which is a very common calculation that is done, you take the liters times the molarity. So those are sort of three ways that we can use molarity or kind of rearrange that equation. And it's very common that you have to solve for any one of those three sort of variables, either the moles, the liters, or the molarity. Now, when we talk about molarity, what that really means is if we can have something that is, for example, 1 molar, and that's what the big M stands for, or how you would say it. So for example, if we had something that is 1 molar sodium chloride, what that basically means is we have 1 mole of sodium chloride per liter of solution. And we can almost use molarity like a conversion factor as well. You could flip it around and go a liter on top is 1 mole of sodium chloride. So you could kind of use these just like a conversion factor. And what that means is if we dissolve something like solid sodium chloride in water, and we would have basically 1 mole of sodium chloride. And if we think about something like sodium chloride, for example, when it breaks apart into sodium ions and chloride ions, which means if we know the molarity of the whole thing, say it was 1 molar, we can basically figure out the molarity of just the sodium ions. And you basically could do it like stoichiometry. It's a 1-to-1 relationship between those two things, which means the molarity of just the sodium ions would also be 1 molar. We could also do that for the chloride ions. The relationship between sodium chloride and chloride is 1 mole to 1 mole, which means that the chloride ions by themselves, if you were interested in it, would also have a concentration of 1 molar. And it does change, for example, if you had, say, something like calcium chloride, which is written badly there, let's try it like that. And when we have something like calcium chloride, when it breaks apart, we get a calcium ion, and we get 2 chloride ions. And for example, if this guy was 1 molar, and we look at the relationship between the calcium and the whole thing, it's a 1-to-1 relationship, which means that the molarity of just the calcium ions would also be 1 molar. But now if we look at the relationship between calcium chloride and chloride, it's a 1-to-2 relationship. So how that basically affects concentration is it is basically twice as concentrated in terms of chloride ions. So we need to take the concentration and basically multiply it by 2. And that would tell us that it is 2 molar in terms of the concentration of just the chloride ions. So obviously 1 and 2 don't equal 1. So concentrations aren't additive in terms of that, in terms of the ions, but it's sort of proportional. So for every 1 of these guys, we get basically 2 of these guys. So there's twice as many of those chloride ions floating around. So sometimes you may be asked for the concentration, not of the whole thing, but you may be asked for the concentration of 1 part versus something else. And you may have to sort of use that relationship. And it's really the stoichiometry relationship, or sort of the mole-to-mole relationship. just to show you how that really works out, is what we're really starting with is 1 mole of calcium chloride per liter. And using the formula as a conversion factor, for every 1 mole of calcium chloride, there is 2 moles of the chloride. Moles of the whole thing cancel. And what we're left with, as we can see on the other side, is 2 moles of chloride per liter. And that is the same as 2 big M. So that's really the long way to sort of work out how do you get to this number. But the kind of short way is you could just think of it as sort of like stoichiometry. So if this thing broke apart into a 1 to say 3 relationship over here, you would multiply it by 3. If it was like a 1 to 4 relationship, you would multiply it by 4. This truly up here is really the sort of calculation as to how you get there by using basically the formula as a conversion factor. Any questions on that? So for example, let's take a look, and if we wanted to calculate the molarity of a solution dissolved by dissolving 15.6 grams in KBr in enough water to make 1.25 liters, what is the molarity? So why don't you give it a try? I'm going to give you some numbers that will be helpful. Potassium from the periodic table is 3910. And chloride from the periodic table is 3545 grams per mole. So once you see what you come up with, we're looking for the molarity here. Take a minute or two to give that a go. While you're working on that, I'm just going to stop sharing for just a second. Okay, so let's take a look here. So we're looking for we're looking for the molarity. And again, that is moles per liter, moles of solute per liter of solution. And in this case, we have 15.6 grams of KBr, KCl, actually. Hope it's KCl. Otherwise, they put the wrong guy up there. It is KBr. That was the wrong one, huh? That's bad. Kind of close. They're near each other, I suppose. So we're actually looking at BR, which is 7990, which would be more helpful, I suppose. Grams per mole. And sorry about that. I got a lot of boxes on my screen. Let's take a guess there. So we do have 15.6 grams of KBr, and that is our solute. And remember, the solute is the smaller part of the solution, while the solvent is the larger part, which in this case, water is the solvent. And we do have the volume of the solution as 1.25 liters. So when we think about this, we do have the liters. This is what we're looking for, which is our molarity. So to solve for it, we're missing moles. And that's okay because we do have grams. So we need to convert grams to moles. And to do that, again, that's our periodic table, our molar mass to do that. So we have KBr, and I got the right elements there. So we're basically going to take 3910 grams per mole. We're going to add it to our 7990 grams per mole. And when we add that together, we get 3910 plus 7990. We get 119 grams per mole as the molar mass of KBr. And again, we're going to use that as a conversion factor. So we're going to start with our 15.6 grams of KBr. We're going to divide by the molar mass, which is 119 grams per mole of KBr. That is going to get rid of our grams. And when we do that, we will end up with 15.6 divided by 119 gets us 0.131 moles. 0.131 moles of KBr. And that is the top part that we need to calculate the molarity. Any questions on that so far? So to calculate the molarity, which is our moles per liter, we just did our moles. So we're going to take our 0.131. We're going to divide it by our volume. And in this particular case, our volume is all good because it's already in liters. So we could just put it right in here as 1.25 liters. Now, when we divide this too, we end up with 0.105. 0.105. Now the units here don't cancel out, so the number always stays with the moles part, and it's always per 1 liter. So you could write it like this, KBr. The other way that you can write it is you could write it 0.105, and you can write the big M, KBr. So that big M basically represents moles per liter. And you could either write it as big M or moles per liter and use both of those units. Any questions on that? So when we talk about sort of that big M, by the way, when we have something like 4.5 big M sodium chloride, I highly recommend that if you are going to use it in a calculation, that you get rid of the big M and just convert it into something like 4.5 moles per liter of sodium chloride. I will tell you that most people, if they leave the big M when they go to do the calculation, they very, very commonly forget all about the liters, or they're not sure where the liters are. Should I be dividing by it? Did they cancel out? Are they still there? So I highly recommend that when you go to use it in a calculation, which is most of the time, probably get rid of the big M, put the moles per liter. That way you can see it, both units, you know where those units are, and you can make sure that you cancel out the correct units, because very, very common people just write the big M and all they think about is like moles. They have no idea where the liters are, where it went, or anything like that. So in terms of the number of significant figures, it's a good question. Let me see if I even did it right. Let's take a look here. So in this particular problem, we have 15.6 grams, which is 3 significant figures. So when we would do the conversion like we did down here, we should end up with 3 significant figures. And then when we divide it at the very end here, that's 3 significant figures on top and 3 significant figures on the bottom. So that should give us 3 significant figures for our answer as well. So that's why we got the 0.105. Other questions on this particular one? Okay, so let's take a look here. That's everything I just scribbled on the screen. All right. Oops. So this is some of the units that we've talked about so far. Again, these are our percentage units down here, our percent mass to mass or percent volume to volume that we talked about, and our mass to volume. And this is molarity. Again, out of all of them, molarity is the most common unit that you do come across. So why don't you try this one? We're looking for how many grams of sodium nitrate there are in 2.5 liters of a 0.15 molar solution. And I'm going to give you the right elements this time, I think, right? So sodium is 2299 grams per mole. And we got nitrogen, which is 1401 grams per mole. And we got oxygen, which is 16 grams per mole. Why don't you take a moment or two? We're looking for how many grams of sodium nitrate are there. Okay, so let's take a look here. In this particular case, if you're not sure where to start, you much like a lot of things can think about what they gave you. So in this case, we do have the molarity given to us. We also do have the volume given to us. So even if you weren't sure at all what you should probably do, the only thing that we're sort of missing here is moles. And that would be a good thing to solve for because ultimately we're looking for grams. So we can go from moles to grams again using our molar mass to do so from the periodic table. So the first thing we want to do is solve for moles. So when we rearrange this, the moles will equal the liters times the molarity. Now, you can look at this, and like I said before, I probably would get rid of the big M and convert it into sort of like a conversion factor. So when you have something like that, you could say that you have 0.150 moles of sodium nitrate in a liter of solution. Again, the number always stays with the moles part and is always 1 liter. And because you could kind of use it like a conversion factor, you could flip it around if you needed to. You could put a liter on top, 0.15 moles of sodium nitrate. So the first thing we want to do if we want to kind of solve this almost dimensional analysis way is we would start with our liters. So since it is in liters, all the units are good. We do want the liters to cancel. So since the liters are on top, we are going to want to use it in this fashion because the liters are on the bottom. And that would give us 0.15 moles on top there. It's right there. Liters will cancel each other out. And if we multiply that across the 2.5 times the 0.15, we will get 0.375. And that unit is going to be moles per sodium nitrate. Any questions up to there? Now, as we were talking about earlier, this is not the answer, right? Because we're not looking for moles, but we are looking for grams. And that's okay because we do know how to go from moles to grams. We do have to use the molar mass. So the conversion factor I think you're talking about is right here. And that is actually the molarity. Yeah. And when we have the big M for molarity, that's basically how many moles per liter there is of something. So when we have this number up here, which is 0.15, what that means is there's 0.15 moles per liter, and you can use it like a conversion factor. You could flip it around if you needed to. So again, when you're doing this type of calculation, I would highly recommend you put both of these units in and use it that way. Because very common people use the big M and they totally forget all about the liters part, not really sure where it is and stuff like that. So when we do have moles though, at this point, again, not what we're looking for. We are looking for grams. So that's where we would go to the periodic table. And again, using the formula and what we see on the periodic table, we would take 2299 grams per mole for our sodium. We would add it to 1401 grams per mole. I'll just draw a line that way for our nitrogen. And then we have 3 oxygens, which is 16 each. And if you do all that, I believe you get about 85 grams per mole as the molar mass. And again, we're really going to use the molar mass like a conversion factor as well. So from our previous calculation, we got 0.375 moles of sodium nitrate. So using our molar mass like we've done before as a conversion factor, we want the moles to cancel. So the moles will go on the bottom. The 85 grams will go on top. And again, the moles will cancel each other out. So we're going to take 0.375, we're going to times it by 85, and that gets us something like 31.9 grams of sodium nitrate. Any questions on where any of those numbers came from, why we did any of that? So a couple of things. What does that number really mean? What that number really means is, for example, if you took like a beaker or something and you put in there your 31.9 grams of your sodium nitrate, and then you put enough water in there with it, and we basically end up with a total volume of 2.5 liters. After all that dissolves as solid and in the water, basically, we will have a solution that has a molarity of 0.15 molar. So that's basically how you would make a solution like that. You would weigh out again 31.9 grams of the sodium nitrate. You would dissolve it in some water, give it a mixy, shaky, maybe not so much shaky, and you'll get all that solid to dissolve. And then you would end up with a solution that has that molarity. Any questions on molarity and the calculation? Also, something to note in these couple of examples that we did, the volume has been in liters, but very, very common, the volume is oftentimes in milliliters. So an additional conversion that you very commonly have to do is take the milliliters to liters, and you do need to convert the volume to liters before you multiply it by the molarity so that the units cancel properly. So a reminder that there are 1,000 milliliters in 1 liter. So that is definitely a conversion that you use a lot with molarity and volume. You could either use the 1,000, move my thing so it don't look like a point. You can use the 1,000 milliliters of the liter, are the same thing as basically moving your decimal point 3 places, either to the left or the right, depending on which way you're going when you do that. So another thing that happens with molarity a lot is, since we oftentimes will measure out volumes in milliliters, you oftentimes has to convert the volume from milliliters to liters. And the reason for that is, if you actually leave it, for example, in milliliters, and you multiply it by molarity, what you get is not moles, you get something known as millimoles. So you get something that's slightly different and off by a factor of 1,000. So people sometimes will multiply by the milliliters, but you then would have to divide by, if you wanted back molarity, you would have to divide by milliliters again. The millis will cancel and you'll end up with molarity back. But for just to be safe, you probably always want to make sure you convert it to liters before you use it with molarity. Any questions on that? All right. And again, that's just all the stuff I scribbled. Probably neater than my scribble, but hey, you get that real life scribble. That's good stuff. So why don't you try this one here? This one is what we were talking about in terms of our concentration of ions. So these are 2 separate solutions. So in each of these solutions, what we're looking for is the concentration of each of those ions based on that molarity. So you want to look at what is in the first one, 1.2 molar sodium sulfate. We're looking for the concentration of the sodium ions and the concentration of just the sulfate ions. And for the second one, we're looking for the concentration of potassium chromate. And we're looking for what the molarity of the potassium is and the molarity of the CrO4 2 minus. Let's see what you come up with, and then we'll talk about it here in a second. Okay, so when we look at this, this is one where we already have the molarity of the actual solution here. So we're interested in each of the parts of the solution, basically the ions that are present. So the first thing you want to think about is how something like our sodium sulfate will break apart. And it's sort of what I wrote up here. When this breaks apart, we will get two sodium ions that will occur, and we will get one sulfate ion that will occur in that solution. And that's really in the solution what is floating around. You really have sodium ions, you really have sulfate ions. Probably none of this guy is still together. The two comes from here, so the two comes out to the front when we break it apart. And again, I'll put parentheses, doesn't need it, but parentheses around this is just one of the sulfates that are basically there. So if we know that the concentration of the entire thing is 1.2 molar, again, this is a case where we can kind of use it like stoichiometry here. There's 1 mole of the entire thing, gives us 2 of just the sodium ions. So again, how that affects molarity is we would multiply it by 2, the molarity of the whole thing. And again, the 2 comes from right here, the coefficient. And when we do that, that would tell us that the concentration of the sodium ions that are floating around in that solution is 2.4 molar. Any questions on that? Now, when we look at the whole thing versus the sulfate, it is a 1-to-1 relationship, which means essentially we're going to take 1 times the 1.2 molar, which will give us, not 2, will give us 1.2 molar sulfate. So the sulfate ions that are floating around is 1.2 molar. The sodium ions is floating around is 2.4 molar. Again, basically, you could think about it. There's twice as the amount of sodium ions, so it's twice as concentrated, which is basically what we see here when we compare these two numbers. It's twice the concentration of sodium ions floating around than there is the sulfate ions. Any questions on that? So for our bottom one, we want to kind of do the same thing. We have the concentration given to us for the entire thing. We want to think about how this guy is going to break apart. And when it does break apart, again, we're going to get 2 potassiums. The 2 coming from here, again, when we break it apart, will come to the front. And that will give us also a chromate that has a -2 charge. And again, if we're going to compare our concentrations, it is 0.75 molar for the entire thing there. When we look at the potassium, it's a 1 over here to 2 relationship, which means the potassium concentration would be 2 times 0.75 molar. And that's going to give us 1.5 molar potassium ions that are floating around. And when we look at the whole thing to our chromate, which is over here, it's a 1-to-1 relationship, which means 1 times 0.75 molar, which will give us 0.75 molar CrO4 2 minus. Again, we see that basically the potassium is twice as concentrated as the chromate in the solution. So as I mentioned before, sometimes you will come across questions where it basically wants the concentration perhaps of 1 ion, 2 ions, and maybe not the whole thing. But if it does in that case, you just basically could think about stoichiometry. So you can think about how it breaks apart. So it's like a 1-to-2 relationship, you multiply it by 2. If it's a 1-to-3 relationship, you would multiply the concentration by 3. Again, looking at those coefficients like we did down here as to how they break apart. Any questions on how to do that? So let's talk about another very common process that's used with solutions, and that is the process of dilution. So when we go through the process of dilution, oftentimes the only thing that's added is more solvent. And a lot of times, as we talked about, a very common solvent that's used a lot, especially for ionic compounds, is water. So very often when we talk about a dilution, it's essentially the only thing that we're adding is water. And, and it's like the sort of soda example. Again, if you get like a big gulp before you come to class and you leave it in your car and all the ice melts, it obviously is not as strong as it was after class, because when all that ice melted, it added more water, kind of watered down the flavoring and all that. And that's sort of the same thing that happens when we do a dilution. The only thing that changes is the solvent, basically. And that means an important relationship is the moles of the solute before and after the dilution remains the same. And when we talk about molarity, which is moles of solute over liters of solution, if basically the only thing we add is more solvent or water, the only number that's basically changing in this calculation is the bottom number. This number becomes bigger. And when this number becomes bigger on the bottom, we're going to take a small number divided by a larger number, and that's going to turn us into a smaller value for molarity. So we'll end up with a much smaller value for molarity because the bottom number here is getting bigger. So as we add more water, this number gets bigger, and small number divided by a larger number will get us a small number. So when we do a dilution, the diluted solution's molarity goes down. So the molarity of the diluted solution goes down from what is sometimes referred to as the stock solution. The stock solution is the more concentrated solution. So the stock solution is the more concentrated solution. So typically we take a little bit of the stronger concentration or higher concentration, we add some solvent to it, the molarity goes down, and we end up with a more dilute solution. That's usually in lab. The type of solutions that you use with most of the time are these sort of dilute solutions. They usually have a smaller sort of concentration. Here's a much fancier way to do it, but essentially we would take a little bit of our more concentrated solution. We would add some water to it in this case. And when we add the water, again, we're increasing the amount of solvent. And in terms of the molarity, we're increasing the bottom part here by adding the water. And that's going to result in a solution that's over here that is less concentrated. And the molarity will go down because of a result of that water that we added. Again, this is what is known as a volumetric flask. Volumetric means expensive usually. They usually have basically one marking, and that one marking represents the volume. So if this was a 500 milliliter volumetric flask, you basically would fill the solution up to that line, and you know once you hit that line, you have exactly 500 milliliters, and usually you would record something like 2 decimal places when you use something that's volumetric. So there is a formula that's used to sort of calculate dilutions and dilution sort of equations, and is what is sometimes referred to as the dilution equation. It is M1V1 equals M2V2, which is what we have here on the screen. And really, this oftentimes is before the dilution. So this is usually your more concentrated values. And this guy is usually on this side after you do the dilution. So this is your more diluted solution. Truthfully, it doesn't matter as long as you keep the numbers together. You can make them opposite if you want, but usually most people go more concentrated here. less concentrated on this side. Now, this is typically the dilution equation that most people use, which is our M1V1 equals M2V2. And that's because, again, molarity is the most sort of common unit of concentration. But in your book and some books, I think you will sometimes see another formula that's basically the same. They will use C1V1 equals C2V2. And what the C stands for here is concentration. And obviously V is volume. As opposed to up here, this is molarity. And this is volume. So you could sometimes use this one as well. It's basically the same thing, because in reality, although molarity is the most common unit of concentration, you could use something like percent mass to mass on both sides. You could use percent volume to volume. You could use percent mass to volume. So all these sort of percentage concentrations, for example, you technically could use in here as well. But probably most of the time, you will use molarity, which again is why most of the time people will remember it M1V1 equals M2V2. Again, it's the same basically as C1V1 equals C2V2. Any questions on that? Typically speaking, this M1 is the more concentrated. And V1 is how much volume of the more concentrated. While M2 is the more diluted guy. And V2 is the total volume of your diluted solution. So your volume of your diluted solution. Now, when we talk about units, in this particular case, when you use M1V1 equals M2V2, as we talked earlier, when we use volume and molarity together, you typically need to convert it to liters. You actually don't need to in this case. You could use molarity and milliliters equals molarity and milliliters. And that's because everything will cancel out okay, because milli and milli will cancel out. But if you want to do it in liters, you can. So you can use molarity on one side, liters on the other, molarity on one side, and liters on the other. So in this sort of application, when you use the dilution equation, the volume can typically be milliliters, but if it is, it needs to be milliliters on both sides, or it could be liters, and then it has to be liters on both sides. And this is different just to distinguish, again, if you are not doing a dilution equation. So if you are not doing a dilution equation, which means you're not using M1V1 equals M2V2, you do need to convert the volume into liters when you use it with molarity. So it does have to be in liters if you're just doing molarity by itself, not in a dilution problem. It does have to be in liters. So if you're concerned about doing it in one spot and not the other, or you might mess up, you could always convert to liters. Then you don't have to worry about it. You'll have it in liters, and you can use it with molarity, and everything will be okay. So again, just a quick distinction. What we were doing before we started talking about dilutions was just molarity and volume by itself. The volume does for sure has to be in liters in order for it to cancel out the units properly for molarity, which again is moles per liter. And that way they will cancel out correctly. This exception over here is if you use the dilution equation, you can leave it in milliliters. It just means that the volume you solve for will also be in milliliters. Any questions on that? Okay, so I think we might have one here perhaps. All right, so once you see what you get here, we want to know what volume of a 19 molar sodium hydroxide solution must be used to prepare 1 liter of a 0.15 molar solution of sodium hydroxide. So I'll give you a second. Why don't you calculate that and see what you come up with, and then we'll talk about it. Okay, so let's take a look. So in this particular case, we have 19 molar sodium hydroxide, and we want to end up with a solution that is also sodium hydroxide that has a concentration of 0.15 molar. Nothing has changed. There's no reaction happening. The only thing is we're going from a more concentrated solution to a more dilute solution over here. They're both sodium hydroxide. So the only thing we're doing basically is going to add some water. So we would use the dilution equation, which again is M1 V1 equals M2 V2. So just to diagram sort of what is happening here, you basically have a bottle over here, a square bottle, that is sodium hydroxide, and it has a concentration of 19 molar. And your goal is to make another new solution that has a total volume of 1 liter, which is 1,000 milliliters. And it also will have a concentration of 0.15 molar. And again, this is also sodium hydroxide. So nothing, has changed in terms of what it is. So we can again use this side as the more concentrated, and this side is the more dilute. So if we put our numbers in, M1 here would equal our sodium hydroxide, which has a 19 molar concentration. Our V1 we don't know, but we do know that the concentration that we want to end up at is 0.15 molar. And we do know that the final volume that we want to end up with for that solution is 1 liter. So using M1 V1 equals M2 V2, we want to solve for V1, as that's the only thing we don't have. So V1 would equal M2 V2 divided by M1. Again, dividing M1 the other side, basically. So putting our numbers in, we get our M2, which is 0.15 molar, our V2, which is 1 liter. We're going to divide it by our M1, which is 19 molar. Again, the molarity here will cancel, and that will leave us liters as our unit of volume, which is good. And we will end up with a volume of 0.0079 liters, or if you multiply that by 1,000, that's the same as 7.9 milliliters of sodium hydroxide. Any questions on that calculation? Now, what that actually means is what we are doing to actually make this solution is, move a couple things out of the way here. What that 7.9 milliliters, I'm just going to do it in milliliters just to make the numbers less zeros. What that means is that's how much of the more concentrated solution you're going to take out. And you're basically going to put it into this new container, and you're going to put 7.9 milliliters of that sodium hydroxide, right? That came out from here. Now, remember that the total volume that we're going to make is 1 liter, or 1,000 milliliters. So the question is, should I put another 1,000 milliliters of water in there? Do you think you should do that? The answer is no, you should not put 1,000 milliliters of water in with that, because if you put 1,000 milliliters of water in there, you already have 7.9 milliliters of sodium hydroxide in there. That would give you a total volume of 1,007.9 milliliters, right? Which you're actually looking for a total volume of 1,000 milliliters or a liter. So that would be too much in terms of the volume we want to make. So we could actually, once we calculate this number here, we could actually figure out how much water we should put in there. And the way you can figure out how much water, which is a very common dilution question, is how much water needs to be added. You basically typically take V2 minus V1. So V2 is your total volume. So again, I'm just going to do it in milliliters to make it a little bit easier. So it was 1,000 milliliters is what we were trying to make. We already know that we put in there 7.9 milliliters of the sodium hydroxide, which means if we subtract 1,000 minus the 7.9, we get something like 992.1 milliliters of water. And what that means is after you put the 7.9 milliliters of your sodium hydroxide from the stronger concentration, you would then top it off with 992.1 milliliters of water. The 992.1 milliliters of water, the 7.9 milliliters of your sodium hydroxide, when you add those together, it gives you a grand total of 1,000 milliliters or 1 liter of solution. So then you would give it a nice mixy, right? Mixed up really good. And if you do all that, what you will end up with is a concentration that should be 0.15 molar. So very common in dilution questions, they oftentimes will ask how much water you need to add. So you want to make sure you read dilution questions really carefully. Any questions on that there? You obviously could do all those volumes with liters. So you would have 0.0079 liters. And then obviously you would subtract 1 liter from it, would give you basically 0.992 liters of water. So you could do the same calculation with liters without converting to milliliters. Any questions on dilution there? Okay, so I think you might have another one to give it a go. So once you see what you come up with here, we're looking for what is the volume of water needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution. Give it a go, and we'll talk about it in a minute or so. Okay, so let's take a look here. So again, we're basically taking our more concentrated solution of calcium nitrate and trying to make a less concentrated solution. So really the same sort of situation here. We have basically a bottle that's more concentrated, which in this case is our 5 molar calcium nitrate. And we're going to want to make a solution that has a total volume, in this case of 500 milliliters, and has a molarity of 0.25 molar. So again, this is our dilution, or M1V1 equals M2V2. Again, here, the more concentrated guy you could call M1. This will be our V2, which is the more dilute, and our M2 over here. So again, the only thing that you're missing right off the bat is V1. So you can solve for V1 just like we did before. V1 would equal M2V2 divided by M1. We would want to put our numbers in. So our M2 in this case is 0.25 molar. Now our volume here is in milliliters. And like I said, since you are using the dilution equation, you can leave it in milliliters. If you want to convert it to liters, that is perfectly fine. It will come out the same, except that you will end up with an answer that's in liters versus milliliters. Here we're going to divide by our M1, which is our 5 molar. So because I did leave it in milliliters, the molarity will cancel. So the units that I will get when I do my calculation will be milliliters. If you converted it to liters, you would get basically the same number, but it's in liters and not milliliters. You'll just have to move the decimal place. And if you do it in milliliters, like I did here, you will get 25 milliliters of calcium nitrate. Any question on that calculation? Again, if you converted it to liters, you would end up with 0.025 liters would be what you would end up with there. Any questions on that? So the question though, and the problem was not how much calcium nitrate, it's actually how much water we're looking for. So again, what this number is, and usually when you calculate V1, what you're calculating is how much of the more concentrated guy you need to take out and put into your new solution. So basically what we just calculated here is we need to put 25 milliliters of that more concentrated guy. Now to figure out the volume of water, we need to take our final volume that we're looking for, which is 500 milliliters. And we want to subtract it from our V1 that we just solved for, which is essentially how much we put in there already. So that's 25 milliliters. And probably should grab a calculator. I can go with 475 in this case. And that's 475 milliliters of water, which again is the answer they are looking for. And a very common question that you're asked in a dilution problem is how much water you should put there. So again, the same idea here. If you were to make the solution, what you would do is you would put your 25 milliliters of water, 25 milliliters of the calcium nitrate in here. And then what you would do is top it off with the 475 milliliters of water. Again, that's going to give you a total volume of 500 milliliters. And if you mix it up really well, you will have a solution that has a concentration of 0.25 molar. Any questions on that calculation? So again, dilution problems, you want to make sure that you do read them because like I said, very, very common. Water is oftentimes what you are asked to sort of solve for. All right, any questions on dilutions, molarity, how to calculate any of those guys? Okay, so to finish up this chapter, which is chapter 7 on solutions. We're going to talk about some properties of solutions here to finish it out. And first off, the first thing we're going to talk about is what's known as the semi-permeable membrane. And basically, it's a membrane that allows certain size molecules basically to pass through. Sort of what the lab is for this week, or you would have done this week. You would have took like a dialysis sort of bag. I'll just draw a really bad sort of idea, but you usually can't see these sort of circles or holes, but you have like a membrane, like cell membranes, for example, or something like that. But you could also do with sort of an artificial membrane, but it's basically got holes in it that allows certain size molecules the ability to pass through. But then, if you get something that's a little bit too big, it ain't going to pass through that hole. So this guy would be excluded from sort of passing through those little holes that are sort of there in the membrane. So it's a good way to sort of filter out certain things. It allows only certain size particles basically to pass through. Now, when we talk about ways to describe solutions, sometimes solutions are described as a colloid. Colloids are much larger than solute particles. And these are large groups of molecules like proteins and big groups of molecules or ion. They're homogeneous, which means they are the same throughout. So remember, that's what homogeneous means, the same throughout. They do not separate or settle out. They are small enough to pass through filters. So when we talk about filters, for example, like a funnel, and you put like a piece of filter paper in there. So you got like a filter paper. And so colloids, they can't pass through these filters. So they would pass through, but they're too large to pass through, say, a membrane like what we got up here. They're basically size restricted from that. There's also another type of way to describe a solution, which is known as a suspension. And a suspension is a heterogeneous mixture. Again, heterogeneous means that it's non-uniform. You see different layers when you look at them. They're really large, as you can sometimes see it with the naked eye. They get trapped both by filters, like on a filter paper, and they also get trapped in membranes, again, because they're really large, so they're not able to really pass through these things. So here's a little picture here of all that. So over here, we got the little circles that are solutions. Triangles are colloids, and our suspensions are our squares. And we see settling of our suspensions. Again, they're really large. Our solution colloids will sort of float around. And if we pour that through a filter, like a filter paper in a funnel, we see that both the solution and the colloids will go through. And if we take something like a membrane here, it will allow the solution molecules to go through, but we see that both the colloid and our suspension are a little bit too large to go through the bags there. So these are typically, what will typically happen. So that brings us to the idea of osmosis. And osmosis, for example, if you had a kind of tube that was separated by a membrane, a semi-permeable membrane, and on one side you had, say, salt water. On the other side, you just had pure water. The process of osmosis is the solvent water molecules moves through a membrane from a lower concentration to a higher concentration in an effort to sort of dilute it, kind of stabilize it. So when we do that, the natural process is the water is less concentrated. Concentration is based on the amount of particles that are in solution. So if you have just pure water, it's going to basically flow into the other side. And it will continue to flow to the saltwater side until it hits something which is known as the osmotic pressure. And basically the osmotic pressure is the pressure exerted down by the atmosphere and the pressure of the solution going this way. They basically equal each other. and that stops the flow of solvent water molecules from, say, the pure water side to the salt water side in this case. And water itself, pure water, has no osmotic pressure. And again, basically osmotic pressure is based on the number of particles in a solution. So something like salt water, which is basically sodium chloride, would have sodium and chloride guys basically swimming around in there, right? And that has a lot more particles than just pure water would have, that just has H2O basically in there. So osmosis is that natural flow of guys from a lower concentration solvent molecules from a lower concentration to a higher concentration. And that's what this is sort of showing. Again, this is the osmotic pressure, the flow of these solvent water molecules in to sort of equalize it will stop when, again, it hits that osmotic pressure. And that brings us to a few different ways to describe solutions. And a few different ways that you could describe solutions is either isotonic, hypotonic, or hypertonic. Isotonic exerts the same osmotic pressure as body fluids. These are typically what IV fluids are. They're basically isotonic. And there are two solutions that are considered isotonic. So sodium chloride, or really any type of salt solution. Sometimes it's called a saline solution. 0.9% sodium chloride, mass to volume, is considered isotonic. And then also glucose, that is 5%, is considered isotonic solution. So these are considered basically isotonic solutions. That means they have the same osmotic pressure as body fluids. And what that means, for example, is if you take something like your classic example of a red blood cell, right? It's got membrane and all that, allows things to go in and out. And if you put it in an isotonic solution, because on the outside and on the inside, basically, of the cell, it's the same osmotic pressure, what you will get essentially is equal flow in and out of the red blood cell. And nothing bad will happen basically to that red blood cell, because water is coming in and water is coming out basically at the same rate, or really solution there is coming in and out at the same rate. And that is different than what we have when we have a hypotonic solution. Hypo means less than, right? And when we put, for example, a red blood cell into a hypotonic solution, so for example, we take our same red blood cell here and we put it in a hypotonic, that means that outside of the cell is less concentrated than inside of the cell. And by osmosis, what's going to happen is all of the solution outside of the cell will essentially run into the cell. You do need to know this stuff. Yeah, you do need to know isotonic, hypotonic, and hypertonic for the exam. Yep. All the solution will run into the cell. That's going to cause the cell to swell and burst, and that is what is known as hemolysis. So because osmosis will make everybody run in, because inside the cell is more concentrated than outside of the cell, we will get basically a hemolysis occurring, and it will swell and burst. And that is different than a hypertonic solution. A hypertonic solution means greater than. And if we take that same red blood cell, draw it down here, and we put it in our RBC being our red blood cell, hypertonic solution. What that means in this case is on the outside of the cell, it's actually more concentrated. So what's going to happen is through osmosis, the cell's going to go, oh, I need to kind of dilute everything that's on the outside. So basically all its water is going to run out of the cell. And essentially what's going to happen is the cell is going to shrink. And that is the process known as crenation when it starts to shrink. Probably not a great thing for the cell, I'm assuming. But that is essentially what will happen in that particular case. Any questions on that there? Now, for us, you do need to know these numbers. These numbers are important right here, yes, that these are your isotonic solutions. If I write a line right through it, that's very bad. But our sodium chloride and our glucose, 5% and 0.9. So that means, for example, if I take a red blood cell and I put that red blood cell into, say, 10% sodium chloride. That means 10% is much greater than 0.9. So that means that this solution is going to be hypertonic. And what's going to happen in that case is what we see down here. On the outside of the cell is more concentrated than the inside. And we would expect it to go through crenation and shrink. And that is different than if I put it in a 2% glucose solution. If I put that red blood cell in a 2% glucose, I want to compare it to my 5%. 2% is less than 5, right? Which means that what we would have is a hypotonic solution in that case. And in that case, that means that we would expect everybody to rush into the cell. And as it rushes into the cell, that is going to cause it to swell and burst and go through hemolysis. Yeah. If I put a red blood cell into a 0.9% saline solution, that means it is isotonic. It's basically 0.9%. Everything's good. Nothing bad will happen to the cell. We'll just make our red blood cell happy. Happy red blood cell, yes. Nothing bad is happening to it. It won't shrink. It won't burst. It'll be perfectly fine. Now, the trick question, right, is what happens if I put my red blood cell in water, pure water? Pure water has nothing dissolved in it, which means it's actually a hypotonic solution. Because it has nothing dissolved in it, it has no osmotic pressure, which means on the outside of the cell, it is less concentrated than inside the cell. And that means that we're going to have the water basically rush in. Any questions on isotonic, hypotonic, hypertonic solutions? You do again need to know those numbers. The 0.9 and the 5% will not be provided to you. Oops, sorry. Go back there. All right, any questions on any of that? All right, so since we're almost to the end here, let's just finish up this chapter. So we'll finish up lecture here in just a minute or two. I think we only got a couple more slides. That way we could put this chapter to bed here. So here's a table similar to one you find in your book about what we just talked about, isotonic, hypertonic, and hypertonic. Again, you need to know those numbers for isotonic. And it's pretty simple. It's either that number or it's too high, which makes it a hypertonic solution, or it's less than the isotonic number, then it's a hypotonic solution. Here's a picture of each of those type of cells. Here's our isotonic equal in and out. Looks like a nice good donut there, right? Here's our hypotonic, where everything is going to rush into the cell, causing it to explode, like our jelly donut. And over here, hypertonic solution, everything's going to run out of the cell, donut hole, perhaps. Yes, as we look at that. Never bad to think about donuts, I suppose. Yes. All right. The last thing we're going to talk about in this chapter is dialysis. And dialysis is a similar process to osmosis. It is actually, I think, the lab that you're going to do this week in person. I think there's now a video perhaps that you can watch. But basically, you can use a dialysis bag like you would have done, and you could put a whole bunch of stuff inside the bag, although you wouldn't be able to physically sort of see the holes. There's basically holes that, much like a membrane, will allow certain things to kind of flow in and certain things to flow basically out of the dialysis bag. And what you're going to do in lab is every so often check the outside to see what floated out of the bag. And then at the end of the experiment, you're going to bust the bag open and basically see what was still inside of the bag. And our bodies, right, our kidneys, right, works for dialysis, right, filters out some things that we don't need in our body and basically works in this sort of process. Any questions on that? Here's sort of exactly what you're going to do in that experiment. You would make a dialysis bag, put a bunch of stuff in, and every so often you would test the outside solution to see what got out of the bag. And like I said, at the end, you would pretty much pop open the bag there and see what was still inside. Here you can see the bigger guys are pretty much restricted from sort of coming out of the bag because there is sort of a size restriction in terms of those dialysis bags. And if I'm not mistaken, that should be the end, as it says, end is good. Any questions on chapter 7? Okay, so a couple of things before we officially wrap up the lecture portion. Some of you were asking about the exam earlier. Again, I believe somebody said the exam, and I'll double check, was scheduled for next week. I don't believe it's probably going to be next week. I think it was scheduled for Wednesday. I think based on where we are in terms of topic-wise, it probably will be moved to the following Monday. And again, it will happen online. We'll talk more about that later as well. And you will take it through our Canvas site, I think is pretty much how that's going to work. And as I mentioned earlier, it'll probably be formatted very similar to our in-person exams. So there'll be some multiple choice questions, and then there'll be questions you have to work out. And again, if there's problems that do have work associated with it, you will have to work it out on a separate sheet of paper, kind of scan it in, and then upload it with your exam. And that way, at least if you get the answer wrong, I still have an opportunity to get you some partial credit and stuff like that. So that's my anticipation as to sort of what's going to happen with the exam. I believe the exam goes through, maybe it doesn't go through chapter 8, does it? Maybe it goes through, actually it might go through just 7, I think. 8's on the next one. So I'll let you know for sure on Wednesday, but even if it's still only to chapter 7, which I think it is, now that I'm thinking about it, which is what we just finished now. It is through 7, right? Yeah, that's what I thought. See, I'm not getting that senile yet because I believe exam 3, close, but not yet. Exam 3, I think, is chapters 8, 9, 10, not 9, 9 is nuclear, 8, 10, 11, 12, and 13, which I think these are the organic chapters. And I think this is acid and base. So that would mean that it's 5, 6, and 7, I think, in terms of the chapters for exam 2. So I'll let you know for sure on Wednesday, but I don't know. I think I might postpone it to the following Monday, but I'll definitely have to double check the schedule to let you know for sure. So technically speaking, we just finished the last material that should be on exam 2. So we could technically take it next Wednesday, but I'm not sure we will or not. I'll let you know so I can get everything together. Monday would be great. All right, we'll do Monday. Why not? I won't look at the schedule. Maybe what is that Monday? That's Monday. April, yeah. So that's April something, 13th. At least it's not Friday, I guess, right? So that's good. So we'll move it to Monday the 13th, and it will cover again, I think, chapters 5, 6, and 7. And that means on Wednesday of this week we'll start chapter 8. I'll say yay too, because it gives me some time to write it and put it online, which is a lot of hours to do. So now we'll start chapter 8, which is acid and bases, and that'll be exam 3. Any questions on any of that stuff? So again, an earlier question was also about the homework. It will still be due the same day as the exam. Again, I'll put an assignment up there on the Canvas site where it's kind of like a Dropbox. You'll have the opportunity just to upload your file. That will essentially be the pictures of your homework that you do. Any questions on that? Okay, a couple other things before we cut out for lecture today. There's the review and everything should all be on Canvas still. So I think it's on the bottom of the module section. So if we go all the way to the bottom is where you can find all the reviews. So nothing has been taken down from Canvas. So everything that was there from the beginning is still up there. And I believe I just had everything up there from the beginning. So I think the exam reviews somehow got pushed to the bottom. So if you go all the way to the bottom, you'll be able to find the exam review for exam 2, 3, and the final as well. They'll be at the very bottom. So we will start discussion in about maybe about 10 minutes or so, 10, 15 minutes. I'll pop it up there. And again, just like normal, if you have questions on any of this stuff, I'll be happy to answer questions that you have. You can pop into the discussion and all that good stuff. I posted something from your lab instructor, I think, about the experiment for this week. She didn't really specify, but I'm assuming as experiment 10, you would probably be the one you should be doing, which I think is the second solutions experiment. So make sure that you do take a look at that. You should be able to hopefully do all that stuff now for sure. And I did get an updated grade sheet from her last week. I just been so busy. I haven't had the opportunity to upload it. So as soon as I get a chance, I will try to upload those sort of adjusted lab numbers that she gave me and she sent it to me. I think last week I asked for it. So unfortunately, I'm sorry, I just haven't had a chance to upload it or anything like that. So I'll try to get that going in the near future as well. Any questions on anything before we sort of sign off here for lecture? Okay, so if you don't have any questions and you're out for today, and I'll see you on Wednesday. If you have questions for discussion, again, we ran a little bit long here today for lecture, but we'll take maybe a 10, 15-minute break and somewhere around, what time is it? Maybe around 7:40-ish or so. I'll open up discussion and you could ask questions. We do have some questions for a bit. All right. Have a good night if you're out, and if I'll see you in a bit, if I see you, and we'll stop sharing. Yes. Have a nice night if you're out. All right, I'm going to officially end the lecture now. And again, I'll start the discussion in about 10 minutes.